Joe, how are you doing?
Excellent. How are you?
Good. So you're in building 112. Last time I talked to you was like 41 or 42, right?
I know, we've moved to the other side of the universe.
Totally,
Completely
man.
different area.
Interesting, but you're still working on the same stuff.
Yep, same stuff.
Cool. And what is that? What's going on?
So I talked about parallel extensions to the Daan framework last time,
Mm-hmm.
which I think after we talked, we released a CTP of. So
Yes.
you go into MSDN and download it. It includes a bunch of stuff. So parallel link, plink, the test parallel library, a bunch of other concurrent data structures and that sort of stuff. So last time I talked with you, I was with Anders,
Yep.
and we stayed at a pretty high level. We talked about some of the syntax and some of the features of the library, but we didn't get too deep.
Yep.
So we're starting to do a series of interviews at your request.
Yeah.
I think it's a great idea to actually dive into the details of a lot of the different technologies.
Excellent.
So we'll start with the task parallel library today. We'll actually probably have a couple of discussions since it's got a lot of cool features. We'll move on to things like plink and other areas that we're focusing on in the future.
Excellent. So we have some of your conspirators here, co-conspirators, some developers and thinkers. Who are you?
Hi, my name is Huseyin Yildiz. I'm a relatively new addition to the parallel computing platform team. So I started working on the task parallel library, making performance improvements, feature additions, and listening to feedback from customers who started using our CTP. And I have a bunch of little bits of information to add here from that CTP feedback. So.
Excellent. How are you doing?
Hey, I'm doing fine. Nice to be in Channel 9.
Good. Now, we were talking earlier, so wait, first of all, say who are you? What's your story?
Well, I'm Daan Leijen. I'm
Okay.
from the Netherlands.
Uh-huh.
I started working here 2 years ago at research.
Uh-huh.
Really enjoying it.
Excellent.
I used to work with Eric Meyer in Utrecht as his PhD student.
All right.
A lot of fun. We did a lot of interesting stuff in the context of Haskell. We did Haskell DB. It's kind of a predecessor of Link. It's really nice to see.
Nice.
And now, when I started working here, I still couldn't help myself, loving combinator libraries and nice abstractions. So 2 years ago, I started thinking about how to do parallel programming in C#. And I built the first prototype of the task parallel library,
Nice.
which I'm really happy to say is now shipping thanks to these excellent people here.
Outstanding, man. It's great to see the Eric Meyer connection extending all the way into this madness.
Yeah, I think Eric's tentacles run deep through the company.
They really do,
definitely
man.
Sure, yeah.
Eric is everywhere.
He is. And Haskell, I tell you, man, for a programming language that's not used by that many people, its influence is pretty big.
Yeah, in fact, Eric's had some to do with plink as well,
Ah.
getting plink off the ground, and so he is actually everywhere.
Excellent. Well, let's first start off as just a reminder what we're talking about here, and then let's dig into this stuff.
Yeah, so I think the best way to introduce what TPL is for people who don't remember is to actually start showing some code samples on the whiteboard
Right
of how
on.
you might use it, what it does for you. There's actually a couple layers of abstraction that gives you from kind of parallel for loops and parallel blocks and sequences of statements all the way down to lower level APIs that allow you to wait and cancel on work. So I figured Dan's probably a good person to introduce how you might use the library and what it's useful for.
Excellent.
So,
All right, Dan.
take it away.
Fine. Well, let's start by a simple example. I guess shall I use the whiteboard?
Absolutely.
Yeah. Well, there we go. So let's start by something really simple. Suppose we have some for loop. Wow, that's it. And right here we have some computation that's actually independent of each other. So we'll do maybe some computation and assign the results to some array. So a programmer might think that this is actually pretty nice to be done in parallel if you have multiple cores. And how would you go about it if you would now be programming in C#? You'll actually have a pretty hard time parallelizing this loop.
Yes.
You would, for example, use maybe threads, but perhaps thread pool would be a better example. But then you have to synchronize them at the end and be really careful. So maybe there's actually a nicer way of writing this. And I think that's what the task parallel library is really about. So in the task parallel library, you would replace this code with a parallel.for statement. So you can actually write parallel.for, and then you give the bounds of the where you want to iterate over. And then as your third argument, you're actually going to give a delegate that's going to be executed for each element here in the domain. So I'm actually going to write, shall I use C#30 syntax today? Well,
Sure.
why not?
Huh?
I hope I can actually do the right syntax. Well, let's actually do a And I think what's kind of nice is that the original code that you were having is exactly the same as you were writing it before, because the C# compiler will automatically capture all the free variables that you're using. So now we're just calling a method with 3 arguments. It's almost the same as your original for loop. So we only have to change really the way we call it, and we have to close the call at the end. And once you do this, the task parallel library will automatically run this particular computation in parallel if you have multiple cores available.
Very cool.
Or sequentially if you just want to use one core, or if you have only one core.
Mm-hmm.
So it also gives you dynamically optimizes for the particular environment you're running in.
So if you have a machine with 16 cores, then you guys are going to do the heavy magic of targeting the cores.
That's right.
And distributing
yeah.
the work using work stealing or whatever else magic you guys are doing.
Yeah, so
right?
actually you're already telling the secret here.
Oh,
we have
sorry.
a very sophisticated work stealing algorithm behind this,
Yeah.
which dynamically adapts actually to even the workload of the machine.
So can we dig into that a little bit?
We can dig into that a little bit, yeah.
It's safe. I mean, we don't want to give away any trade secrets.
I think I'll actually suppose, for example, that each computation here is actually highly irregular. So maybe for compute 1 is really quick, but compute 2 is really slow, and compute 3 and larger is quick again. So if you would statically distribute the work, so you would say, well, run the for every I, run it on core 1, 2, 3, 4, 5. Then one of them will take so much longer than the rest that everyone will basically be waiting for that single one. So with the work stealing, you will dynamically distribute the work. So core 1 may actually do task 1, 3, 4, 5, 6, while core 2 is completely dedicated to the slow computation. So in that way, it will dynamically change its ways. And I think another nice thing is that often you're not running on a dedicated test machine, but you're actually running on a desktop machine, and your virus scanner is working on one of the cores. Another core, Office is loading something. You may actually be running your compiler in the background, so you don't have all these cores available. So actually statically scheduling the work is really impossible. And the work stealing algorithm behind the TPL will dynamically adjust to the workloads on the machine to make the most of the processing power that is available.
Interesting. Something that's worth noting too is the parallel for construct is really just a shortcut. It's actually, the implementation of parallel for is actually pretty small. It's actually built on top of other abstractions like this task API that we provide. And you notice that parallel for spawns a bunch of parallel work, and it doesn't return until all of that work is done. You might wonder how that's done. It's because it's built on top of these task abstractions that allow waiting and cancellation. And so it's probably worth getting into a little bit about what tasks look like and what the fundamental building blocks that parallel for loops are built on top of. And then from there we can probably dive into a little bit about work stealing.
Cool.
Yeah, shall I?
On the spot again. Yeah.
Okay, well, shall I? I'll write down the basic task API. Maybe that's a good idea. So really, fundamentally in the library, there are only 2 abstractions that we are exposing, and it's tasks and parallel replicable tasks. And these 2 things, all the other abstractions are built on top of that. And that means that if you get the semantics right for these 2 basic items, you get a semantics right for all these other abstractions too. And it's very important in a concurrent setting. So really the basic interface is a task interface. How do we write it? And there's a few methods which are important. And one of them is, I think we use create nowadays, right? So we have a static method. return to task. And it's a creation method. And to create a task, we'll just give it some work to do. And there will be a delegate that actually performs it. And we call that an action. So we can create a task by giving an action, and then the task will be potentially executed in parallel. Up to the point where you actually say, now I really want to have the result. So there's actually a method on this which is called a wait method. So you can actually call wait on one of these tasks, and between its creation point and the point you call wait, will this action be executed, potentially in parallel.
Now, that's important that you keep stressing potentially in parallel. I mean, why else would I want to use this library unless I wanted things to run in parallel?
So the TPL is not so much for, it's really for if you have a big computation and you want to speed it up as much as you can on the multiple cores. But it's not about fairness or asynchronous programming. It's really about speeding up computations. So you, as a programmer, you're really exposing potential parallelism such that we can speed up the computation for you. But we do not guarantee this parallelism, because that would imply a much more heavyweight mechanism. So now we can be really smart about scheduling this.
Excellent.
So I could go into that a little bit, why it's so
yeah, that would be cool.
So maybe I have a really nice example called the Fibonacci function. It is maybe somewhat too simple, but it definitely illustrates the problems. Shall I?
Please, I think everyone definitely has that understood.
This guy
Good
out.
old lambdas, right?
That's actually a good point. One of the nice things about C# 3.0 is it makes writing these little inline actions in the parallel for bodies really simple. I mean, it makes it look almost identical to what you would have written for the sequential code, which
Absolutely.
is part of the power.
Getting that functional stuff into the imperative world.
In fact, you can access these, not to pick on C++, since I know a recent interview did a good job at that, but...
I love C++, don't get me wrong. That was Gilad.
I do too.
Yeah.
I do too.
Gilad's an opinionated dude.
But it turns out C++ doesn't have closures, right? So if you try to use all of this library, which you can for managed C++, it turns out to be a little bit more verbose, because when you're creating these delegates, you don't have the nice inline lambda syntax. And so it really shows off kind of the expressiveness of the new lambda syntax. And in fact, just anonymous delegates like C# had before.
Sure.
You try to use this from C++, it's a little bit more painful, but it's certainly doable.
Cool. So, I mean, that's an important point that you just stressed. I mean, can you use this library for C++?
Yeah.
You just have to do a little more work, a little more sort of...
Yeah, I mean, it's not that much.
Massaging of the structures.
You just need to type a little more our arguments, right?
Yeah.
For your actions.
Yeah.
So.
And you can even use link from C++. I mean, not a lot of people do it, but when you have plink, it becomes a little bit more attractive to do that. So
Cool. So they should make sure they use shared pointers, and which is that's actually a really nice TR1 feature that I talked to those guys about recently. All right, so we have the Fibonacci example. I guess one question I would ask from a design perspective is the notion of doing this in a library and not in the virtual machine, if that makes it. So in other words, what I'm saying is, so you say parallel for. What about if you had like a keyword you could use that said, so in other words, if you, anyway, so I guess what I'm saying is it'd be interesting if there was a language feature where you could say, just like you could say atomic, and then run code, and that's what software transactional memory people are working on in their Haskell implementation. But anyway, I
think it's really interesting what you're saying, and it's always a trade-off, right? Are you going to do deep language integration with new keywords, or are you going to first give out a library where you can express the same issues, but in a slightly heavier weight way? And personally, I think the library allows us to experiment with all these new parallelism abstractions, to see what patterns are mostly used, to fine-tune the design. And I think it's not clear yet what would be the best way of doing these things.
Sure.
And with this library, we're really going to actually find out what would be the best way in the end to integrate this maybe into a language.
Outstanding.
But at the moment, I think a very nice point about C# that's not often realized is that the combination of generics and delegates, the higher order functions, and first-class lambda expressions, we're really able to express a lot of things that you would usually express as new statements or really extensions to the compiler. You can express them in the language as a library in a very lightweight way, which really, I think, allows a whole new class of libraries in C# that would otherwise not be possible.
True.
And I think we've seen that happening a little bit with the Haskell language that allowed this for the first time.
Mm-hmm.
And you see a lot of these kind of libraries called combinatorial libraries for parsing, for concurrency, for pretty printing. And I think we'll see the same kind of libraries come into existence for C#, with the TPL being one of those.
Excellent.
It's also important to stress what Dan said. It's lightweight. A lot of people will look at a library solution and say, oh, well, it's a library, so it's obviously more heavyweight than if it were implemented in language, which isn't actually the case. I mean, the language implementation would probably just compile down to use of this library. There are some minor optimizations we could make around stack allocation versus heap allocation, but they're all kind of minimal. So people shouldn't be frightened of using it simply because it's a library.
Oh no, not at all. It's just that what I'm saying is that it would be interesting to see purely in a vocabulary context or grammar, to not have to do instantiate an object, call parallel.for. I just simply say, for whatever you're doing, and then somehow I have some way of indicating to the compiler that I want this to be run in parallel if possible.
Yeah.
That's all I meant. I'm not.
No, it makes sense.
All right, man. So that we got sidetracked as usual.
Yeah, that's right.
My
Well, I
fault.
thought actually before I go into the Fibonacci function, I'll explain one other concept. It's kind of nice. It's an old trick from other functional languages like Scheme. It's called futures, which you also support. And those are really tasks that you don't just compute because of their side effects, but they're actually going to return some value. So these are tasks that are generic in some.
It's called future now.
Oh, it's called future. Oh, I love it. I love it. Okay.
That's a cool name.
See, it's kind of funny. Dan originally had Future of T in the library. When we first picked it up, we renamed it to Task of T, and now we're back to Future of T. So
Back to the future, man.
Vindication.
yes, back to the future.
Hey, there's somebody else walked in here.
Yeah, sorry to join late.
Yeah, you're a slacker. You're the slacker of the group.
I'm
huh?
the slacker of the group.
So what's your story? Who are you?
So I'm Steve Toub. I'm the PM for the Task Parallel Library.
Right on.
Parallel extensions in general.
And you've been scheduling all these, and
I've
much
been scheduling
appreciated,
all these.
man.
My pleasure. My last meeting ran late, so as they normally do.
Right on. All right.
Okay, yes, I'm a happy guy that now it's, I can actually call it future. Very nice. So what you actually say is, I'm going to compute some value t somewhere in the future. So when you create this guy, you give it an action that returns some particular value of type t, and you get back immediately a future of t. And at a certain point, you can ask for its value, and the value will actually implicitly do a wait. So you're sure that this future will be done by the time you call value. So it will be somewhere executed between the time you create it and the time you call value on it. And potentially in parallel again.
Nice.
This is a very powerful concept, especially if you use pure functions over here without side effects. We'll come
Is
to
that
that later.
possible in C Sharp?
You have to be very careful.
Okay. All right.
I think it would be interesting to mention that it won't always be in parallel, but it could just execute where you look up the value, right?
That's
so
right.
If the future isn't executed until that point, so
That's actually a really important point that Huseyin is making. And I think it's like the crucial item that makes the library efficient, and that's why I'm always stressing it's potentially in parallel. And I'm gonna show that with the Fibonacci function,
Okay.
or the parallel Fibonacci one. So we probably all know the Fibonacci function. So the Fibonacci of n is really the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. And we use this example to show how you can quickly create many parallel tasks. And it's really about computations on trees that go in parallel on both branches. So here's how I would write it in the parallel library. So if n is smaller or equal to say let's say 1, then we're just gonna return 1. Return n probably, right? Yeah, I'm gonna return n. And otherwise, we would really like to do the Fibonacci of n minus 2 in parallel with the Fibonacci of n minus 1. So we're going to do those in parallel. We're doing one of them as a future. So we're going to write the future will be an integer of the Fibonacci of the n minus 1 will be future create. Okay, and then we're going to give a delegate expression here for what's going to be executed. And you don't have to take any arguments, and we're going to return pfib n minus 1.
Mm-hmm.
I think in C# we can leave out the return argument nowadays. So,
And the semicolon at the end of the.
and the semicolon at the end, so we actually get a fairly nice expression if I would have had more space on the whiteboard here.
And it turns out we do some magic with the static classes we expose, so we'll actually infer the type for the create method, so you can even get rid of the of int for future.create. But
That's actually nice, right?
really getting clever.
So let's
Nice.
actually do it, completely C# 3.0.
And then, yeah, exactly. I was going to say the var keyword, let the compiler infer the type for you.
Nice.
There we go.
There we go.
Beautiful.
So we
Very
create a
nice.
future here. So we're going to know that pfib n minus 1 will potentially be done in parallel. Well, we can just as well do the Fibonacci of 2 ourselves directly. So we can call pfib n minus 2 ourselves. And then by the time we're here, we're actually going to be interested to see that this future is now done. So we could say, what we're going to return, that's the Fibonacci of n minus 2 plus the value of this guy. So we do f1.value. I think this is the crucial part. When we call value here, we now want this pfib n minus 1 to be calculated. So now suddenly you expose a lot of parallelism because this is a recursive function. It'll basically do all the n minus 1 ones potentially in parallel, and each of them again, right? So you quickly create hundreds of thousands of parallel tasks. And you have to be very efficient in the library to handle those kind of numbers. And the library can. That's a nice thing. And I think here we come to Huseyin's point where he said not every task is done in parallel. And this is the really, I think, the core of why the TPL is efficient. So think about implementation. So what will actually happen is that when I create a future, I will put it on, I will advertise this particular computation as being available, and it can be done by any core that is idling, there's no work to do. And they can steal basically this task. So by the time you end up here, either someone has stolen it and already finished it, then you're in a great position because f1.value will immediately return with your result, and you have achieved the maximal parallelism. Another thing that happens a lot is that no one has actually stolen it. It's still on your local queue. It's just sitting there. No one was idling, and no one was able to do it. Happens a lot if you create hundreds, thousands of these guys. But in this time, I actually know how to calculate the value. Because I call f1.value here, I will just sequentially start executing it at this particular point in time. So at this time, there's no thread switching, there's no strange things going on. You will just immediately sequentially execute it yourself. And that will happen most of the time, because only in the beginning you'll maybe create some parallel tasks that will be spawned off on another core, but after your 4 cores are being used, you can just as well do all the others sequentially yourself. So this is a very important case.
So one thing that's worth pointing out, so it doesn't look like we're cheating, it does turn out to be the case that at some depth in the recursion, you often want to stop creating these tasks because even though we make them as lightweight as possible, a task is still an object allocation. There's some overhead to a task.
Yep.
We will strive to make them as cheap as possible, but you still need to think a little bit about, especially these recursive divide and conquer style situations. And we're currently investigating ways to handle a lot of this internally to the library, but for now it's something that developers have to at least keep in mind.
I think another point worth making is that in this code sample, Dan did have to take some care in the order in which he created his operations. He's no longer just doing the same thing with the left branch as he is with the right branch. If he were to move his p-fib of n-2 to before he created his future, then he's creating the future and immediately waiting on it and entirely serializing his whole operation. Versus what he's doing now, which is spinning off the asynchronous work before he does the work serially after that, which allows this entire tree to be asynchronously created. And so you still do have to pay some attention to how you structure your program and not just willy-nilly start throwing these features in and so forth. But it does make it very easy to kind of input this asynchronicity and concurrency into your applications with this really cool future mechanism.
Also,
Excellent.
we considered adding an implicit coercion between feature of t to t instead of you having to call value. But we figured it might be a little bit too much magic going on for exactly the reason Steve mentioned. You know, if it's not obvious when you're actually waiting for the value, you could accidentally introduce concurrency at the wrong point and wait on things when you didn't expect to. So
That's interesting. Yeah, that's a great point. I mean, I could see, you know, you're trying to make things easier for people, but they still have to think.
Exactly.
You know, after all, we are talking about engineers, man.
Yeah.
We're skilled. All right, cool.
That was actually a good point that Joe and Steve were making.
Great point.
That you still allocate something here on the heap. So in practice, it turns out to be very quick, but you have to do enough work here to offset the allocation, and usually that's more than just. So for for a small n, there will be just very little work being done, just some additions and maybe some tests. It's too little. So in reality, you would really have the threshold will be something like, if it's smaller than 10, I'm actually going to do the sequential version. I'm going to return the sequential Fibonacci of n that avoids any of these allocations. And that's something you still, as a programmer, has to deal with.
I think we actually have examples of that in our CTP.
We do.
So if you download the CTP and look at, we have a bunch of samples in there of how to use the task parallel library plink, and they actually show in there how to use this kind of sequential threshold cutover.
And I think it's worth pointing out, especially in this case where Fibonacci, there are obviously better performing implementations of Fibonacci than a recursive solution, right? There's ones that are sequential, there are ones that are non-recursive, there are ones that are, you provide an exact formula to come up with an exact value. But the general approach, and the reason Dan's chosen the Fibonacci solution, is that it does exemplify this typical recursive implementation where you're recursing over or occurring over a tree, whether implicitly or explicitly, a data structure or not. And so in the CTP, there are very, very similar examples that use a quicksort, for example, where it's the same sort of thing. You're breaking the current problem into smaller subsets and processing those subsets recursively, and the exact same solution applies.
So it kind of might be worthwhile switching gears a little bit.
Sure.
So there are some APIs we didn't get into. For example, Task Manager allows you to actually create separate pools of tasks that are isolated from all others. You can attach different policies to them. The parallel APIs actually have more to them as well. So there's a parallel invoke that you can pass an array of delegates, and each one can happen in parallel. But since work stealing keeps coming up, and we alluded to self-replication earlier, maybe it's worth getting into a little bit of the implementation, how it all works. You know, parallel compiles down to tasks, and tasks compile down to use of this work stealing infrastructure, which we really haven't gotten into yet.
Yeah, maybe we can do one more thing before we go in there and show parallel do.
Before we dive into the rabbit hole?
Before we dive into the... I think because parallel do is kind of a nice example of how you can create your own abstractions. So when we just saw the Fibonacci function, Steve is already pointing out you have to be careful when you create the future and what you do at a certain point in time. But it's actually fairly easy to create your own abstractions. And I thought I'll show you at least one of them is parallel do. So you have a static statement called parallel.do. And you can say, well, what can you do in parallel? Well, for example, two actions. So you can have two actions action 1, another action, action 2. And how would you implement it? Well, you would create one task, T, that does, for example, action 1, potentially in parallel. So you'll do task.create action 1, and then you're going to do action 2 yourself in sequentially, because why would you allocate for that? And then you'll just wait till task 1 is done. And that will be it. So now you've created your own little abstraction where you can do 2 actions in parallel, like in the case of Fibonacci. So you really created your own structured abstractions only. And this is what I meant by the combinator libraries, that because all these things are implemented as a library and first class available, you can really create also your own, capture your own patterns that you see a lot and write them down in the language itself. I think that's a pretty powerful way of designing these things, and that's actually what we use in the real product too. Like we said, there's only a few abstractions, and all the others are really built as small wrappers around it in these forms.
Excellent.
One of the nice things that Parallel does for you that it's kind of skipped over in the simple example is exception handling. So I think I touched on this last time, but in a parallel world where you have many things happening at once, unfortunately many of those things can fail at once. And unfortunately that kind of changes the way exception handling works, because if you were executing this parallel do action 1, action 2 serially, then of course if action 1 threw an exception, you could just prevent from calling action 2 altogether. You would just throw and not ever call it. But if you're running them in parallel, well, if action 1 throws an exception, it could be that action 2 has already begun running, possibly even through its own exception. And so we handle that by all of the APIs, parallel for each, parallel do. We aggregate these exceptions up into this kind of, basically it's an exception, which is a collection of exceptions. It's called an aggregate exception.
Aggregate exception.
And much like all other exceptions that have an inner exception property, it has an inner exceptions property, plural, which is actually just a collection of the exceptions.
Interesting.
It changes things a little bit. It's one of the things that is kind of a fundamental shift in the way that you write your code when you switch from sequential to parallel execution. And we have a lot of convenient APIs and ways we think will make it easier to deal with that, but something to be conscious of.
Absolutely. So are you thinking developers would actually implement an aggregate exception object?
Well, we
in their
implement it
class?
for them.
Okay.
So it's just a matter of what they do with it if they ever catch one.
Right.
So we have ways of actually catching it and finding whether a particular instance of an exception occurred within it. We don't have any currently in the CTP, but we are working on tool support to make it easier to deal with these kinds of exceptions.
So if you wrap the code you just did right there in a try catch,
Yeah.
what am I going to catch is my question. Would I catch aggregate exception and then?
Well, I can kind of show you. So, say you have, and I'm not calling this version. I'm calling the one that's in the library today. Parallel do, and then you have throw foo exception, and then throw bar exception. I should note that this exception handling model is consistent across all of the parallel extensions library, including plink, because plink again runs into the same fundamental issue. So somebody calling this, if they say try, the question is, well, what are they going to catch, right? They might want to write catch foo exception, catch bar exception, but as 2 separate catch blocks, but the problem is they both might happen. And that's completely different from how exception handling works today. We don't run multiple catch handlers for the same try block. That's just not the way we do things. So what we do today is if any of these throw an exception, we will throw an aggregate exception from parallel do. It's just a matter of what it contains. So I'll just abbreviate aggregate exception AE. And basically AE has an inner exceptions property, which will contain either a foo exception or a bar exception or both exceptions. And so conceptually what happens is when one throws an exception, you can view us as trying to go out and stop the world so that no additional exceptions happen, but we still can't prevent the fundamental race condition that exists. And so basically the catch handler here needs to, either it needs to handle the particular kinds of exceptions, or you just let it escape up the call stack. And kind of the best practice that we're guiding people towards is to actually not let exceptions leak out of parallel actions, to actually handle them in line. So if you actually did the try catch in here and write what you would have written outside, then you can handle it however you'd normally do it. It's just a matter of what happens if this code can't sufficiently handle the exception. Then you need to communicate it out, in which case it's probably fatal, so you're probably not going to try to catch it right away. And so you're probably just going to let the thing go unhandled and kind of blow up, show them top level message handler and that sort of thing.
Here's one comment on something Joe said for those folks who read Joe's blog and know his rants on thread aborts and thread groups and the like.
Come on, man, we're all friends.
They're wonderful rants. They're brilliant and they're fabulous to read. But he speaks eloquently on why they're bad things. And so when he said stop the world, it's not like we go off and we thread abort all of these other things that are happening. We try and prevent them from running. If they're already running, we'll allow them to run to completion, although we do support mechanisms for letting them know, hey, we would like you to stop if you can, and then that we can kind of cooperatively cancel operations that are in progress. So I'm not trying to get down on you for your rants. I think they're great. I'm just trying to clarify it so that there's no confusion.
Excellent.
So I just want to add a small point about Joe's suggestion for handling the exceptions within the user's delegate as much as possible. So that doesn't quite apply to the parallel for construct all that well. So the idea is that the delegate is executing continuously. So it's probably better to keep the try catch blocks outside the. Does that make sense?
Yeah. I mean, sometimes you want to terminate the for loop and you want to communicate that out of the for loop, much like you would in a sequential program. So really, these are just best practices, and you can follow them where they make sense or break them when they don't. But I just wanted to point out that it's a little different.
Cool.
I think
Thank you.
An interesting thing with the exceptions is that it's actually another form of side effect. And if you want to do parallel computations, you really don't want to have side effects. You want to have your side effects isolated to the things that can be done in parallel. And the moment it's unchecked, so that means we actually do a lot of work for the exceptions, but you can still have race conditions, for example. So if people use parallel do or parallel for, they have to really be sure that the things they are doing can be done in parallel. And usually that means limiting your side effects. And that was, I think, what Joe was saying. It's much better to handle the exceptions within your parallel parts, so it's unobservable to the rest of the world. And I think another common thing that could happen that's actually wrong is that they both assign to the same variable. So I can show it actually with this guy. So I see exceptions as one effect where we actually do a lot of work to still do something reasonable. But in general, you could also do other kinds of effects. So you could, for example, write int x equals 0, and I'll do x plus plus over here. And I'll maybe do x plus plus over here too. Well, what will be the value of x at this point? Well, it will be really hard to say. If I do this sequentially, it will be 2. But suppose they both run in parallel and they both read at the same time. They both read a 0. Now they're going to both write back a 1, and then x will be 1. So this is a really bad situation you really never want to run into. So if you've ever shared state and you want to do things in parallel, you better put locks around it to protect them. And that's something we don't check for at the moment, although it's something we want to do. So at research, in my group, we're working hard to do analysis that prevent you from even writing these things.
Okay.
Where we actually include analysis to see if exceptions can escape from here. In which case you can give a warning or point the programmer to it. But it's still work in progress. At the moment, as a programmer, you have to be careful.
Sure.
You can do this, of course, if you properly put a lock around the access.
But then, of course, the usefulness of something, of introducing parallelism, depending on how much you're locking, becomes a real issue, right? And so, and obviously you're using this just as an example, but in this particular case, if you end up locking around your plus pluses, this is going to be significantly slower than just doing it sequentially. So you definitely have to be careful. And so once you start introducing shared state, as you have in this case, it's a very difficult road to go down.
So I mean, just to rat hole a little bit on the notion of education. Most people haven't really done a lot of parallel programming, right? Because we've weaned people sort of on the, here's a big giant base class library and a runtime and new languages and go build these things. Mm-hmm. And now we get the fact that hardware has evolved to the extent where this matters. How are you guys educating people, besides just throwing out really cool libraries and saying, but remember, don't do this? Because to some developers, say, business developers, they don't think about shared mutable state, right? You guys kind of think in those terms.
Joe's book.
Read Joe's book, man. Read his blog.
It's not out yet, so you can't actually read it, but a couple months.
Right. Cool.
I don't know, I would say a couple things. First, we really push people towards, well, we don't push them, but we encourage them to use P-Link, because P-Link is very functional in nature, and so while yes, you can do side effects and you can do really nasty things, the programming model guides you towards writing more declarative code that's functional in nature. It doesn't deal with side effects, and so you have to take a conscious effort to jump outside of the safety that P-Link gives you by default. And so that's a great place for people to start, especially people who don't really grok shared state and mutation and that sort of thing. I think over time you'll see a lot more of a focus on educating people on how to build immutable data structures. And if you read a bunch of the C# team's weblogs, Eric Lippert has recently blogged a bunch about immutable data structures. I encourage everybody to go read that. And Purity too. I think we'll educate people about these things over time. Hopefully tool support and stuff will come online later as Dan's research progresses. And
Cool.
No pressure.
Yeah.
But I think the absolute best resource for education on this kind of stuff is Channel 9.
You think so?
Yeah, absolutely.
Right on, man. Good.
So should we jump into work stealing?
Sure. I mean, definitely.
Yeah.
I mean, now, one thing that's kind of important for people to understand here is this is all written in C#. Everything that you guys do, even down to the threading level, right?
Yep.
Just want to throw that out there.
Yep.
Cool. All right. And you're still performant.
Oh yeah.
Well, it depends on your definition of performant, but we like to think so.
Well, we do have this funny benchmark where we use an hand-optimized matrix multiplication. How you would write it currently with a thread pool in the best way possible using interlocked instructions. And we do the naive matrix multiply using the parallel.for, and they both use the same algorithm, of course. And there, the parallel 4 always beats the one that's written using the thread pool, and that I think is a pretty good achievement.
Absolutely.
In the end, of course, it always depends how much performance you get in practice on the algorithm, how much communication you do, the memory layouts. It's more usually the algorithm that determines how much performance you get. But at least you get as good a performance as you would otherwise be able to do by hand. I think it's crucial, actually, if you want to make a library with a high level of abstraction, that your underlying primitives are really efficiently implemented. So shall I show it a little bit? Or?
Sure.
Yeah.
It's all you, Devin.
Okay. Well,
You're the only one here from Building 99.
the new fleshy building.
He used to sit in this building, but now he's in the better building.
Yeah. I moved up, and you too.
we got the hand-me-downs from you, though.
Actually, it still says Microsoft Research on the front of our building.
It does, actually.
Yeah.
So that's an important point. I mean, for the people out in the audience following Microsoft, Building 99 is the new quote-unquote high-tech building that research actually helped design, apparently.
That's right.
And
Up to a certain point.
yeah.
I had many ideas about swimming pools and stuff, but I never went out the way I wanted it to.
Interesting. But I was over there for the Jim Gray tribute. That was my first time there, and it was that's a pretty impressive building,
Yeah.
for sure. All right.
So, how does it work internally? So the library is not about fair scheduling. It is just about trying to do as much computation as possible. And it's a really important point. So in our case, we try to schedule only one thread per processor. That's our nirvana. So we have a thing I call worker group, and we have one there's connected circularly. So one of these things is called the task manager. You can create actually many of them depending on your needs. And then each task manager can take up a bunch of resources. And in this case, you would say, I'll pretend to have 4 processors. So I'll schedule 4 worker groups for each of these processors. And then the invariant is that I only try to have one real OS thread running per processor. And that's the best thing you can have, because it would mean the OS doesn't have to schedule between threads. And every thread can run full speed on every processor, and you'll have maximal performance. So what you actually do is you schedule one of these threads inside a worker, as I call it. So each worker group has a bunch of these workers, where one of them is running. So actually, there could be more threads per worker group, but then there's always all of them are blocked except one. So one thread is running per processor. They're doing all the work. And then each worker group has a local queue of tasks it still has to do. So again, these are per processor. So in the Fibonacci example, it will recursively call itself all the time, and it will push all the n-1 tasks up to these local task queues. It's really important that it's local, because it would mean I don't have to communicate with any other queue. I don't have to take a lock on a global task queue. I can just push it on my local one, because I'm the only one accessing it. So this worker that's doing Fibonacci will push up all these tasks and basically advertise themselves. And keep running and running, and then when it actually hits the value or the weight for a task, it often sees the last task that it actually has pushed on its own local queue is that particular one. So it knows, I can actually directly execute it myself again, because no one has stolen it, and it will be running as long as it can. And these other worker groups are kind of doing the same, and they also have their workers. But of course, these workers have nothing to do. Their queues are empty, they have nothing to do. So what they will do is they go on stealing mode and steal some work to be done. Instead of nice items, they steal work. They're very eager guys. So they go around, and then they find on this guy's local task queue, they'll find all these Fibonacci n-1 tasks that are still waiting here. They'll steal one of these, and then they start executing on their own local processor. And they will generate their own Fibonacci task, because it's all branching out, pushing it on their own local stacks, and keep executing. And they'll just go. So only when they have nothing to do, they'll actually take a little round trip to see if they can steal something.
So now, just out of curiosity, how do they know about the existence of the other tasks?
So
what's the underlying knowledge mechanism?
So they're all connected by a linked structure in the memory, and we assume shared memory. So in each processor, they actually look at the other guy's queue to see if on top of their queue there's something to be stolen. Okay. And I think there's a really smart algorithm at work here, because these queues, they'll look a bit like this. And now people steal from this end, right? They can steal this particular task. But the own worker, he's pushing on this end of the queue. Now if there's enough distance between these two guys, you can actually do these things without synchronizing. So here, the stealer always has to synchronize, because they can all be stealing at the same time. So there's slightly more synchronization involved. But this guy can often avoid doing any real synchronization. And that's crucial to make it fast. There shouldn't be any synchronization. The only reason why parallel programs run slow is when they synchronize with each other, when they have a lock or a handshake between them. So this distributed task queues really make sure that you can do as much local as possible, as long as you can. And it's really, it's a key property to make things more efficient. So the reason why sometimes we have to create more threads than just one per worker group is that sometimes you actually, you suddenly want the value of your Fibonacci n-1, but it's stolen, and it's not done yet. Right? So it's somewhere else, and someone is working on it. and now you don't know what to do anymore. So in that case, it will block itself, and we'll use another thread from our little local thread pool to start working here. So we maintain the invariant, only one thread working per processor, but now we have one blocked thread sitting here. And again, if someone goes idle, he'll also look for the blocked threads, and may discover, oh, this guy can actually start running again. Why not, move it over to me, and we'll run it there on that processor to continue it. So there's a lot of details in doing this scheduling algorithm in the right way, but it definitely works really well. And it's kind of an older idea. It's actually implemented in Silk language, and these guys also proved that this kind of work stealing algorithm behaves on average best, given all the worst case scenarios you can imagine. So there's no strategy that works, for all possible workloads better. So there's both good locality and both worst case behavior. So I think that's an important thing, because in the end, the parallel libraries, they will run on desktop machines. As I said, your virus scanner, your office, your game.
Sure.
It has to be very dynamically adapting to the workload. And you cannot assume a certain static division of work. I think that's a point people often do wrong. You see some textbook matrix multiply. They say, 4 cores, I'll chop it up in 4 parts, my array, and do 4 computations. Really bad. One of them may page fault, the other 3 are done. This guy still, you have to maybe wait 10,000 cycles before it finishes. One work item takes 10 times as long. You're all waiting. So you have to make small work items and dynamically distribute, because you really don't know where you're going to end up.
Absolutely.
And I think you see it actually more in the distributed world with MPI, where they try to solve these problems.
Now, is there any sort of the guys who wrote the core algorithm that you based this on weren't dreaming of a world with 80 cores?
Well, they were
right?
dreaming of it.
Okay. So do you see
they never had one.
They never had one, so it hasn't been tested. Do you see there being any potential sort of maximum number of possible,
well, I
cores?
think it's already the case that these algorithms that we're using are more sophisticated than the ones you can find in the papers. But I mean, they're based on the same ideas. But you could definitely notice that just the lack of hardware impeded, more sophisticated designs.
Sure.
So is there a limit to the number of cores? Well,
we'll find out, huh?
Yeah.
Well, I think actually more. When you talk about limits, it starts to become more of an issue in the applications and the programs that are using this infrastructure, not in the infrastructure itself. One of the problems with the current CLR thread pool is that it's not based on a design like this. So there's a single global lock, there's a single global queue, and as the number of processors increases, that simply doesn't scale. This is great because it distributes responsibility of queue management to the rest of the processors, so it's all processor local. Now it becomes an issue of, can you actually write applications and algorithms that utilize all of this core? And there's something called Amdahl's law, which is pretty well known, which basically states your maximum speed up to do with parallelism is limited by the maximum amount of sequential code you have left over after parallelizing. Right? So if 80% of your time is spent executing sequentially in your program, then you have a little small bit that is parallel. Well, yeah, you'll shave off at most 20% of the execution time, but you're still left with that 80% sequential execution. And you're not going to get rid of that simply as a result of having multiple cores. So it really becomes imperative that you try to find where you're going to get the maximum bang for your buck. Where's most of the time of your program spent? Is it this one for loop that is doing processing 90% of the time? If so, that's great. I mean, you're going to get tremendous speed ups. It will scale terrifically. And in fact, I think, Dan, didn't you look at some MSR project where the bulk of the time was spent in one for loop, and you made like a one-line change, and the thing scaled almost perfectly?
Well, actually, it was more of a counterexample. It was one of these a real program that does graph layout. I think it's actually shipping now in Visual Studio for the schema designer.
Cool.
And we changed one line, and the graph algorithm speeded up a lot. But still, there was still a lot of time spent in just building up to the UI, reading the files, getting everything set up. So we couldn't achieve much more speed up than about 2.43 even on 8-core machines. Even on a dual core, it would almost be 1.8 times as fast. So the first cores made a lot of difference, but then afterwards there was not enough parallelism really to make a big difference anymore.
Yeah, I think it's easy to see graphically. Too.
Yeah, that's right.
If you draw, say this is the execution time of your program, and this is the sequential execution time. So sequential time is this, and then you go ahead and you rewrite your program so that, say, a chunk in the middle is parallel. So you're going to parallelize this part, but these two parts are going to stay sequential. So what do you have? You basically have sequential, and then maybe you reduce the parallel time to something like this because this is highly parallelizable. You slice it into chunks and basically stack it up, and everything runs in parallel here. You still have this sequential portion remaining, and so as you can see, you can have infinite number of processors, and yet you still have this time here spent doing sequential processing. And so you throw more cores at it, unless you start to chop off other parts of your program that are parallel. And throwing more cores at this is not really going to make you go faster.
And it shows the first 8 or 16 cores. They're really important. Right. But after that, unless your entire program is parallel, the benefits are going to be much, much less.
Although I do like to point out when you're talking about Amdahl's law, and Amdahl is kind of the pessimist or the glass half empty kind of guy, and then Gustafsson came along with Gustafsson's law, which basically says, yeah, this is a true picture, but what if we could expand this? What if we could make the size that is currently the P on the board, the parallel, what if we could make that bigger by, for example, throwing more data at it? So over time, as we get our applications process more and more data, or in the example of graphs, if our graphs got bigger and bigger and bigger, the portion
is a great example there. Right?
Games, exactly. The portion of the application that is parallelizable becomes bigger and bigger, and so as we throw more and more cores at it, the percentage of the application that is parallel grows and grows and grows, and thus we can parallelize in a sense more of the application. So it's not changing what Amdahl said. It's sort of a corollary that says, yeah, if we can't change this factor, what if we can change that factor, and how will that result in improved performance over time?
That's a very optimistic way of looking at things, but there are the very real examples where you are stuck with a fixed size problem, yet your hardware keeps growing. So in those cases, there's a tiny little detail here which becomes important. As you keep parallelizing, there is a certain overhead to parallelizing, because you have some coordination going on, some allocations to manage. In the end, those become kind of non-negligible and start adding up. So I think the important point here is that the users should be aware of this. I mean, sometimes they need to limit the number of cores that they are running on. So, so it's not a silver bullet, I think, what we are providing.
Yeah. Well, I mean, but this is all great stuff. I mean, you'd want to run computation in parallel, right? When you think about computers or computing, so I'd want to run. So if I have a UI intensive application or something, there's going to be certain chunks of it where running in parallel doesn't make any sense. But when I do computations, spread it out, get the work done, so I can get back into my user experience mode in the case of, say, Office or whatever, a general purpose application.
It's a great point. I mean, if maybe the bulk of your programming time, or the time your program spends, is actually painting the UI or doing some goop to do with the GUI, but if you're parallelizing the response to button clicks and the user sees a perceived difference in the response time from sequential execution to when they upgrade to their new 16-core box, say it goes from being 16 seconds to index some document to being 1 second. I mean, they're going to notice that difference, and they're going to be incredibly happy with it.
Sure.
And so that's what I was saying earlier. You really need to understand where the biggest bang for the buck is going to be and focus there first, which requires probably some understanding of performance and doing profiling of your application and that sort of thing.
And I think the library really helps you again, right, to express the potential parallelism in your code in an easy way, and that's what it does. It doesn't magically make your
solve all the world's
better.
problems.
That's right. No, it doesn't. No, but I think it really helps you if you have one of these P parts to make it quicker. And you've seen rather big programs where you just have to change a few lines. Usually there's some outer loop, some outer thing where you can identify the chunks that can be done in parallel. You can easily experiment with it. You just import a library, change a few statements, and see what happens.
True.
And I think that's an important advantage of the library.
But now in the model of like VB, which is a definitely an honorable model of the notion of a machine that does a lot of work for you. It would be kind of interesting in the future, the far future, for runtimes to be able to do this kind of assessment, understanding for me. Basically, the compiler knows what I want to do, right? Sort of. I mean, don't get me wrong. It's not science fiction.
No, and I think there's been a lot of research into that automatic parallelism, like discovering that this parallelism available and actually using it.
Mm-hmm.
It has been especially done in the context of languages like Haskell without side effects, where you can basically do any computation in parallel for sure, and it's safe to do so. But I also have to say lots of this research has not worked out as well as you may hope.
Sure.
And it seems like a really hard problem, and I would be surprised to see it ever working in practice. And I think it has a lot to do with determining the overhead, like what is the smallest thing you could do, and it would still be cheap enough to actually do this work. All the little things going to add up in the end. So it's but yeah, it would be great if it ever pans out.
But in reality, back on Earth, this is very cool.
So one other thing I think for the future, I think we're really looking into is also asynchronous programming. It's another thing. You would just talk about an OK button, but I think it's something that really at the moment is a problem in practice. And maybe multiple cores can actually help in that domain too. And one of the models I'm currently working on myself is thinking about the futures of T, where you say, well, in the future it delivers some value. You can also think about certain asynchronous operations that in the future will deliver some value. You can already do the request, basically, and only later really ask for it. So we're now looking into extending this basic design here to incorporate these asynchronous methods.
And actually related,
keep tuned.
Related to that, I think we're going to talk with Daan Leijen in an upcoming episode where he's doing all this F-sharp asynchronous workflows and that sort of thing.
Yeah.
We're actually working with Daan right now to get all that kind of using our library. So
outstanding.
Should be ready to talk about that soon.
Very
upcoming
cool.
Weeks.
Great, man. And that's of course is F-sharp.
Right.
Which is a functional language running on top of the CLR.
Right.
Very impressive stuff. It's been productized.
I know.
Right on, Don.
Well, it's not done
very
yet.
cool.
It's in the process.
It's in the process of being productized, but it got the Soma blessing.
It did
and that's
get
a
the
very
Soma
good
blessing.
thing, man.
So, well, hey, this is part 1, right? So we'll continue and get deeper into other areas for part 2.
Yeah. And hopefully, if people want to see anything in particular, they can respond on Channel 9, and we'll focus on those in the future. That would be
Great. Well, hey, that's great. You heard that here, Niners. So rather than, when you make a post on the thread, ask for what you want them to talk about next, and we'll do it.
Precisely.
Hey, it's great talking to you guys.
Thanks a lot.
Thanks for having us.
And very impressive work.
Thank you.
Thank you very much.
Thank you.